truss with main link. Let us first consider our three-hinged truss. The three main hinges here are A, C, and B. We recall that all joints of the truss are hinges, but really C is a critical hinge because a cut passing through it separates the truss into two completely separate parts. Here we have two supports, one at A and the other at B, and both are hinges. Let us test the stability of our truss. We have to count our members, our joints, and our reactions. Let's first start with the members. We have member 1 here, FG, 2, 3, 4, 5, 6, and 7. 7 members at the left of C, and they are repeated identically right of C, so we have 14 members. Let us count our joints. We have 1, 2, 3, 4, and similar 4 at the left part, so we have 8 joints plus one common joint at C, which makes 9 joints. We have 2 reactions at A because it is a hinge and 2 at B, so our reactions are 4. The unknowns are the number of members plus the number of reactions, because we have for each member one internal unknown, which is the force in the member, and our external reactions are also unknowns, so we have 18 unknown. Our equations are 2 multiplied by the number of joints. This is because at each joint we have 2 equilibrium equations. Sigma forces in the x direction equals 0 and sigma forces in the y direction equals 0. Since the equations equals the unknowns, therefore our structure is stable. But let's consider A is a roller. This means that we reduced our unknowns by 1. We have 3 reactions and we still have 14 members, and the number of unknowns now is 17, while the number of equations remain 18. So the equations are greater than the unknowns, therefore our truss is unstable. Let's see what can happen. We have our unstable truss here. A has the total freedom to move horizontally, and C has a total freedom to move therefore vertically. So the result is a failure of the truss. Collapse of the truss. Now our truss here needs an extra unknown. Let's consider this unknown to be an internal force, extra internal force. So we really need a link member to join the left part of C with the right part of C in order to avoid this failure. We have here our unstable truss. We add a link between D and E. Of course, we would have added this link between A and B, or any other link joining the left part of C to the right part of C. Let's consider our reactions now. We have 1 reaction at A and 2 at B. Taking sigma moments about A equals 0, of course we have the blue forces are the external forces, the green forces are our reactions, and dimensions are shown on the truss. We will consider our equation sigma moment at A equals 0, so the forces cancelled here are YA, XB of course because it's extension or really it passes through A or has no arm about A. The 10 tons at F also has no arm about A. Those are the forces that don't appear in our equation. We are left with 10 tons at C with an arm 8 meters, 10 tons at I with an arm 16 meters, and our horizontal 4 tons at I rotating in an opposite sense to the previous forces and therefore minus 4 by 8 minus YB by the arm 16 meters until we reach A. This gives YB equals 13 tons and we plot it on our diagram. Considering equilibrium in the Y direction or in the vertical direction, of course we have 10 blue vertical tons taken just in one shot in our equation, 10 multiplied by 3. We previously computed YB and this gives YA equals 17 tons and we plot it on our diagram. Equilibrium in the X direction equals 0 gives XB equals 4 tons and we plot it here on our diagram. This was the idea of the truss with main link. DE is considered a main link. We note that DE is a clue member as many other members in the truss won't be able to be calculated unless we have the value of DE. So, good practice to start with is to have a cut passing by DE and separating the truss into two separate parts to be able to calculate the internal force in DE and then easily proceed with other link members of the truss.